Me to perfect.
Yeah, just
Awesome. Thanks.
okay. So, hello everyone. I'm Or Zilberman, Mr. Iguazio, and I'm going to talk to you a bit about MLOps and about MLRun, which is our open source solution that should allow you to very easily move your work from training to production and do experiment tracking, and essentially enable you to easily integrate MLOps and best practices for data science in your work, so you can move your work, as we said, to production in a much easier way. I'll start off by going over a few slides and presentation, and then I'm gonna quickly go over to show you some code, show you MLRun, and how we can actually use it in order to deploy our projects into production easily. Okay. So the first thing, okay. So the first thing I want to talk to you about is really what is the problem that we see and why do we actually need MLOps and why it came to be. So as we can usually see, most data science projects are phased into two different steps, the research and the production phase. Essentially, in the research environment, usually we have a data scientist, he gets a project. It can be any kind of project, classification, regression, deep learning project. But what we can usually see is that in the research environment, the research phase of the project, the data scientist gets a data set, usually either a CSV, a small sample of the data, maybe a small sample of a few images, something that you can work on. Usually they work on it locally or either in some EC2 in the cloud, which is the development environment. And in this development environment, usually working with Jupyter or some small scale tool, we develop a model and we end up evaluating it locally based on this data set. So if we think about it, we have a process that is running usually locally in some way, even though maybe on some EC2 in the cloud, on a Jupyter notebook. And when we end the project and we got a goal, we got to this, let's say 80, 90% accuracy and everyone are happy, we really end up with some model file, usually that we can, yes, that we can integrate maybe later into a system. But there is a lot of difference between this model file and Jupyter notebook that we may have now to a full-fledged AI system that is running in production. Think about the difference between the model file and, for example, the path prediction at Waze for your GPS that lets you know immediately which route you need to drive to and how it scales up and really is answering millions of requests per second. And we can see that there is a full process that is behind that, and we need to make it happen to really deploy our model into production. And usually it is incorporating things that we do not take into account always or need to simulate when we work locally. So we receive the sample of the data, but when working in production, we need to worry about things like real-time ingestion of data, streaming data, coming in from multiple sources, usually multiple database, each one with its own purposes. We need to do our pre-processing and all the data preparation at another scale. A lot of the times it's even done with different tools. We can see people working on models and doing things on scale and locally, but they end up need to be deployed in Spark. Sometimes even there are different like development teams engineering teams that are deploying things on totally different technology and rewriting everything from scratch, just so it will be able to handle the loads and what is needed to really create that. After that, the training part, we trained at a small scale, but now maybe we need to do some distributed learning, either by using tools like Spark or Dask. If we're doing deep learning, maybe we need to engage with technologies like Horvath to be able to do multi-GPU, multi-node processing. And after done all this training, we need to think about how we serve the model. Like we said before, like with the Waze example, you have millions of requests per second. You need to really incorporate your model and deploy it in such a way that we'll be able to really scale with the load and handle it. Because at the end of the day, the best model in the world, if no one can use it, we didn't do much with that. So, okay. So usually those differences really are, we can say, coming in those different categories. As we said, we develop the models. Usually for a team to develop a new model can take a few weeks. You got some task in a sprint to update a model, or maybe do some new baseline or update a new model. We end up with our model file, and from there we need to package it, worry about things like Docker and build parameters and requirements, the scaling, load balancing, the model and the endpoint, distributing the model and scaling all the different resources. We need to tune it or fine tune it, add things like caching in this process. And if we talk about really production ready model, we need to worry about monitoring of the model, in case something happens to the endpoint itself and we cannot reach it. And even in qualitative forms, to see things like content drift, and that our model is performing just the way we want it to perform with its usual performance. Logging, so we can debug and also see and explain it on how our model is working. Versioning and security, of course. And to make everything easier, we really want to automate it all. This is also where a lot of the MLOps practices come in, to have a CI/CD for all the different tests and testing, to have workflows to run the entire training pipeline and deployment pipeline for us. We want to have nice ways to upgrade our models and to push it without need for any downtime or special handling by a lot of different teammates. We want it to be done seamlessly, and even be able to do things like A/B test for the new models that we have, see that what we see in the lab really impacts our performance currently. So now moving to show you a bit about MLRun itself. Are there any questions? Meanwhile, okay. Okay, so I quickly want to go and dive into a bit of code so you can see MLRun actually how it's running, and also to talk about some best practices. So what I'm going to show you now is one of our demos. All our demos, MLRun demos, are available on GitHub in MLRun demos. You can just clone it and use it with MLRun and run them on your own system. So MLRun has two sides. One is about the experiment tracking and tracking all the different jobs that we run. which comes from our project screen, where we can see all the different projects that are running. I'll go into it while we show the demo, so it will all be in context, don't worry. And the second part is the actual MLRun package and how it enables you to really orchestrate your code, get functions, and deploy them easily. So what I'm going to show you now is walking through a simple project done with MLRun. This is an sklearn-based project, and it's going to be about some easy data set, the iris data set. It's mostly about really showing you how MLRun can help you to really deploy a model and make it viable in production. So we first off, we start by, of course, importing MLRun, and we will create our project. So this will be the SK project, and we can set our MLRun environment. Essentially, what we're going to do is have this project name, and we're going to define an artifact path for it. The artifact path is where all of our different artifacts, like the models and the plots and the data set that we have, are going to be used. And this will essentially configure this project for us, so everything will be on top of this project. Now, as I said, this demo is going to be around iris data set. We're going to walk through all the different steps in order to execute this project. The first thing we want to do is really to get the data set. This comes to mimic as getting data set from some online source, some CSV, sitting on top of S3 somewhere, or any available data source that you have. So we have this simple function, the iris generator. It's going to load the iris data set. This can come from the sklearn data set. We're going to create our pandas data frame and log them into MLRun using this log data set function. When we will run this function, essentially MLRun will give us this context object that we can use to later log everything. We can log a different line, add it to our debugging, and as we said, log data sets, and later we'll see how we can even log different models. So I've defined my MLRun project. We have a function in our notebook that we want to run, and now we can run it locally through MLRun in our Jupyter notebook. We'll use run local. We'll give our function as a handler, and when we run it, we can immediately see this new added line at the bottom. Essentially, MLRun added us this DB line, which tracks the projects. Each run has its specific run UID. We can see different labels and inputs parameters that were put into the function. And we can also see in the artifact list, this iris data set that we logged from before. I can even click on it and see it right here. If I go into projects, I can see my SK project. I can see my SK project, and of course this one was already ran, but I can go into my files, and I will have my data set as part of all the other tracked file here. I can also see how I ran this function, the iris generator function. The iris function, all the different labels, the artifact that was created, as we said, this iris data set with a preview. I can see the log that I saved for before, and if it's deployed, the actual code for it. Now, the next thing we want to do, after we've seen how we can run this function locally from our Jupyter notebook, we want to see how we can run it on top of our Kubernetes, on top of the cloud. Usually, if you want to deploy a function like this and deploy it on top of Kubernetes, we need to create a Docker file, a Docker image, and think about essentially on the necessary infrastructure for it, create a YAML for the pod, and a lot of other nasty words. But MLRun makes it easy for us, and in order to run this function on top of my cluster, all I need to do is use this code to function. Function, we have the function name, and I need to specify the function kind, which is a job. Job essentially will allow us to run this function once and on top of the cluster. And I can add this function as part of my project functions. And once I've done this, this function will also be versioned for me. So if I go back into the dashboard, I can see that I have my function reference, and I can even see the code of this function. So everything that we do through MLRun, every time we run a function, everything that we do is tracked, and including the code, including the data and the artifacts. So we immediately get a lot of this benefit and the ability to run our functions immediately on top of the cluster. So if you're working on a small laptop, we can test whatever we need here, and then supply, for example, the full data set, the bigger one, and run it on top of our Kubernetes cluster using just one function. Another part that MLRun helps us is really in this ability to import code very easily. So we've seen this code to function and how it can turn this notebook, extract the code from up here. We also have this small annotation here for the encode. This is how it knew to only take everything that shows up to this cell and turn it into a function that we can run on top of the cluster. And in the same way, we can essentially get any file that we have, any Python or any kind of notebook, and do the same, make a real function out of it that can run on top of Kubernetes or be distributed later on. You can also specify different archives like zip or tars, and even directly specify a GitHub repo. In this case, it will take the code directly from GitHub and deploy it to the function. In that case, all we need to do is essentially specify the handler that we want, which will be the file name in our repo that we want to get to, and the function that we want to deploy. If you want to see more about this, of course, you can go into our MLRun docs, and you can see how to run all the different jobs directly here with all the Git and zip examples for you. So we said that we can get things directly from GitHub, and in order to make it even easier for you to develop, we have the idea of Function Hub, which essentially is, we can think about it as a marketplace for functions. You can even define your own hub. And once you define it, you can call all the different functions from it directly, like this hub and the name of the function. Automatically, by default in MLRun, it will grab all the functions from the MLRun Functions repo. I advise you can see a lot of different MLRun functions available here, including some that are very nice. You'll see in a moment, like an sklearn training function, sklearn training on top of Dask, model servers, drift function, and so on. And if we actually look at the function that we want to get now, it's the describe function. We can see different documentation, the code that was made. We can see the function YAML, which is essentially what MLRun creates on the backend so we can run on top of the Kubernetes, and a notebook containing how to run the file. And as kind of a best practice, I advise you to break your functions into different notebooks or different files like this. It will enable you to really manage everything in a much nicer way, version all the functions independently and edit them. So every time you share between maybe your data scientist team and data engineering team, every change can be version tested and applied in the fastest and smoothest way. So back to our topic here. We've gotten our data. We have this Iris data set. The next thing we want to do is some EDA. We would like to describe it. Like I said before, we're going to very easily grab this describe function that we made before from our repository directly from GitHub. We can see the documentation that we wrote for it, and this is also automatically being created for us. So if you document your functions, you will automatically, it will automatically create the documentation in MLRun 2. So we can see this documentation, and this time we want to run this function on top of the cluster. So all we need to do is really, to get our describe function, we will apply a mount. Mount essentially allows us to look at the files on top of our Kubernetes cluster and run the function. Now, all we need to do is to supply the parameters. The parameters are essentially all the different attributes that we have and our inputs. Now, what are inputs? Inputs are an MLRun construct, a data item. Essentially, it allows you to get version and tracked files. In this case, we're going to get this Iris dataset and get tracked objects directly from MLRun. It also allows you to easily download files from the web. For example, if you have your files on S3, and as with enterprises, there is a lot of security. You can add all your different secrets to MLRun to the project, and then whenever you will give us this S3 address, it will just download the file for you without you needing to actually handle with all the connection and authentication to S3. Same for any link to any file, CSV, Azure or GCP, same address. So one more nice thing that you can immediately see is that as a reference to our Iris datasets, we didn't even need to give it the actual address of the file. All I needed to do is give it the reference coming from my generator function before, simply specifying this Iris dataset output from my gen function, which we ran before. And because we tracked this and logged the dataset as Iris dataset, I could immediately get it as part of my outputs. So running this, we can already see that this was running on top of this cluster, and we got the pod that was actually created for it on top of the cluster. We can see all the different artifacts, like the different histograms that were created about the data, correlation matrices, imbalance weights. We can see the different inputs. We have our table here, and you can see that this is a store artifact. This is a sentence coming in from MLRun. And again, this is all tracked to the describe function, the inputs that we had, which is essentially the artifact coming from our get data function, that is data set with its own unique version. And we can see all the artifacts that were created, the histograms, the plots, and everything that this describe function saved for us. We can see the log, and we can even see the different pod parameter for the pod that was running on top of our Kubernetes. So just to sum this up, essentially we had a function that we wrote, we saved it on top of GitHub. We've got this file using one line and ran it on top of our Kubernetes cluster with another line. So in two lines of code, you got a function, some code actually coming from Kubernetes, and already ran it on top of your Kubernetes cluster, version, and track. Now we can add all the other functions that we need for projects also from our hub. So we have the sklearn classifier, is essentially a function that, given a data set and the labels, will train the data set. A test classifier to test our performance, and then we're going to deploy our model into production and create an actual endpoint that we can serve our model with using Nucleo, our serverless function framework, which I'll talk to you about in a minute. And then we want to really test it, see that our endpoint is live and can receive and give predictions just like we want. So now that we have all these functions in our project, the next thing that we want to do in our MLOps way is to create a pipeline that will chain it all together and run it as a single unit. We want to have a pipeline that will be able to take us from the start of getting all the data, the latest data set that we have, run our describe function to let us know all the parameters of this new data set, train the model with some hyperparameters, give us the best model, and test it, see that it is actually performing like in a training data set on some other test set that we have, and deploy it to production, providing us a live endpoint of the new model. To do this with MLRun, we need to define a pipeline function, what we call a workflow. So there are two functions in our workflow that we need to define. We need to initialize it. Essentially, here we add our mount to the functions if needed. We can also add some kind of special parameters that we need for our functions. We can specify it here. And the actual pipeline. Now, what MLRun will do, MLRun is going to read through this, parse it, and be able to run it on top of Kubeflow pipelines. So we have our pipeline function. The pipeline function can receive arguments directly from here, so we can change and make every run with all the parameters that we want. And how we generate this pipeline, all the functions that we've saved into our projects are available for us through our funcs object. We just need to specify the name of the function and run as step. When we run as step, we need to specify our run parameters like we did before, which function we want to run, what is the name of this step in our pipeline. If there is a special image for Docker that we want, we can specify. If it's already specified in the function, we don't need to. The parameters that we want, and the outputs that we expect. So this is our ingest function. After that, we said we have our describe function. We want to run our summary, and it will get the labels, and it will also get the output of the ingest step. Now, defining this lineage, MLRun will automatically parse it and create the right computational graph for you. So just by parsing and seeing how the outputs are being received as inputs in other functions, like this train function, we have our hyperparameters. We're going to try 3 different models, select the one with the maximum accuracy, and as an input, we receive the output of our ingest step. So just defining this will make the ingest run first and our training to run after that. Then, as I said, we're going to test our function with our test function. This will receive our model from the training step and the output, the test set that was splitted in our training function. And then we will deploy this model into production to be a production candidate and test this endpoint live. So we've written this, and now we will set it as a workflow in our project. This will be our main workflow, and we can save our MLRun project. Now, to run this workflow, all we need later to do is project.run. We can give it the arguments that we want. We can tell it where to save all the different artifacts and files it created, and MLRun will run it for us. We can see the results of all the different runs. We can see the model tester and the training. We received like very high accuracy and all different artifacts. But we can also see directly the pipeline that was created. So this is our pipeline. We have this get data. We have this get data function, and then our summary with all the visualizations, our training function, which created the model. You can see all the results, the test function, and then our deployed model and model tester. And if we go into our actual project, we can see all those functions here. We can see how our model tester worked. It ran 15 tests. We can see the results. We can see the test on top of our training data as before, see the results, the artifacts or the confusion metrics, the feature importances, and any other kind of data that we want. And like we said, this is all version for you. So every time you run the function, you can see all the different artifacts that were linked to this specific run. So if you change your code at all, this really enables you to track your best performing run and use that. So essentially, if we'll conclude what we see in this notebook, we see how we can define an MLRun project using our set environment with the project name and the artifact path for the project. We saw how we can take code from a notebook up to our Nucleo and code, and using code to function, turn it into a function that can be run on top of Kubernetes. While MLRun, if needed, will build the different Docker images for us, or we can simply supply with the image name that we need. We saw we can take code or functions directly from our repos. So we can, like in our MLRun functions example, we can create different functions, save them, version them, and work with best practices on top of Git, get them to our project, run them with one line on Kubernetes, including things like lineage and the artifact tracking between our functions. And how we can easily also take all the functions from our projects and create different workflows, automated workflows that will run on top of Kubernetes, be versioned, tracked, and even enable us to really deploy an endpoint function. Okay. Are there any questions about this? Okay, great. So the next thing I want to talk to you about is our model serving part. I talked about it briefly here, that we deploy the model, but we really wanted to help you guys with MLRun to deploy our models quickly into production. And we created a construct that is called our serving runtime MLRun serving, which really enables you to very quickly put your models in production. And I quickly show you an example with our model server. Okay. So, as I said in the start, one of the problems that we have really is deploying our models to production. The big difference between the model file that we get when we end our training process and the actual endpoint that is scalable, monitored, and can really run on scale. In order to solve this, what we've done is we incorporated Nucleo, which is our serverless function framework. This is an enterprise-grade framework, open source. You can go to Nucleo.io or GitHub. Nucleo, this project has about 4,000 stars, and it is used by enterprises in many places. We've incorporated Nucleo as a backend and created a runtime that enables you to very quickly write your logic and deploy it. So in order to deploy the model that we've seen before, our scalar model, essentially all I need to do is to write this classifier model class. And this classifier model class, which is created from our V2 model server in MLRun, only needs two definitions in order to run: how to load your model and how to predict with your model. Since these parts are what requires a lot of the logic and changes between different frameworks, maybe you need some extra files, some files with parameters, normalization, or even just some list of classes in order to make your response prettier. All you need to do is to write your class, tell us how to load. In this example, we will get our pickle model and we'll simply load it with Cloud Picker. Now, since the model was pickled, it will work directly. And to predict, we'll just take our body, we'll get the inputs from this body, and the JSON event that we are getting to the function with the features, and use model.predict. And that's it. Once we've defined this classifier model function, in order to deploy it just like we've seen before, we'll use our code to function. This time we'll use the serving kind. We'll give it MLRun's base image, MLRun. And now we can just test it, deploy it, we can get our iris model that we've trained before. And once we hit function.deploy, it will build the function, put our class in that, and deploy to production, and it will receive an actual address on top of our cluster that we can now hit and deploy. And we can easily test this function. We have our own invoke, so you don't need to really remember the address by yourself. You can just invoke the function. The URI, which is matching for KF serving and Triton servers and the regular serving APIs, V2 models, the model name and the function we want, and this time I want to infer or predict, we'll give it this sample data, and we can see that we receive the response from our model. And if we go to a project, we can see with MLRun, we have the real-time function. This will essentially guide us to our Nucleo dashboard, which show our V2 model server function. We can see this class, my classifier model, was deployed. There is some extra code here. This is essentially given to us by MLRun when we deploy. But we can see how we took the code, configured everything, and now this is actually live on top of our cluster. This is, as I said, enterprise production grade endpoint, and essentially we could list this also with different triggers connected to our Kafka, so it will connect to a stream and start to immediately send and receive events, run it with some cron, connect it to a stream, or like we currently have our HTTP endpoint. We can see the status for it and all the different monitors too. Okay. Are there any questions about this part, MLRun serving? I will also point out that everything under serving and data pipelines, you can also find here. We have our serving graphs. Create your different serving pipelines and serving functions. Like this example here. Okay. Any questions? Okay. So the next thing I want to show you, we talked a bit about sklearn. We talked a bit about sklearn, but now I want to show you a bit of a harder use case, we say, how we can run distributed deep learning training with MLRun using our another runtime that we have, MPI job runtime. So, like we said before, we're going to show how we gather a data set from online, train a model. This time it will be distributed on a cluster, and at the end deploy our serving function and test the endpoint. So what we're doing in MLRun, we're going to use a horovod created by Uber. It enables you to do multi-node, multi-GPU training. So as we said before, the first part, as with all the other MLRun projects, we're going to specify MLRun, start the project. In this case too, we have our get dataset or open archive function. This time we're going to get our archive URL, as I said, as a URL. And essentially this will construct our training folder from the zip file. So it will be created with the training and validation directory and all the labels in a nice way for TensorFlow to run. And when we finish, we will this path. We can just directly log this path where we saved all the files as a target path, and it will log it for us. So we want to run it on top of locally or on top of the cluster. Like before, we can put our target path as a parameter, and we'll use MLRun's input mechanism with this zip coming from S3 in order so we can just get the file, download the file easily. Just so we can see, I can simply use MLRun's .local on top of this file, and it will download it for me. And if we define the secrets and security measures for MLRun, it will do it automatically for us. Okay. And now, as we said, the more interesting part is really running our distributed training. So we have a Horovod file, a TensorFlow training file right here. Essentially, this is normal TensorFlow code. What we've added here is this MLRun context. Since this is not running from a function, but a standalone file, we need to create the context. It's not given to us as in the functions that we run, but we just use it to get the different parameters for our run, like the directories and some parameters like the epochs, batch size, learning rate, and everything we need to run our training. Other than that, everything is normal. We check for GPUs, and if they're available, we will use them. And we define our model. This is a ResNet 50v2, which will define. We will add our Horovod optimizer, so it can distribute the gradient between the workers, and do some pre-processing and run the training as usual, we can say, without model fit, using some prefetching and batching of the files. And when we ended our training, we will log everything to MLRun. We will log the different results, like the loss of our function, the accuracy that we had for the validation, the test set, and at the end, we will log our model. Now, the nice thing, we can log our model, we log our file, we can add different labels to the model, we can add our results, and also add all the different plots or any type of data or file that we think that should be versioned with our model together. And now that we have this file, as we said, we want to run this in distributed manner using multi-node, multi-GPU in order to train at scale. So all we need to do for that is to create a new function with MLRun. We will supply this file as our command for the function. It will essentially just treat it like the file name and grab it. And this time, we're going to specify our kind as MPI job. And when we use the MPI job, it will know to run it on the distributed runtime on top of our cluster. We tell MLRun how many replicas we want this function to run with. This is essentially the number of workers in the different nodes that will be used when we train this function. And we can add per pod, per worker, how many CPU, how many memory, and if we want, how many GPUs should be attached. So we can create any kind of configuration that we want to train with. For example, 2 workers, each with 1 GPU, or the opposite, 1 worker with 2 GPUs can also work, or anything that our infrastructure can actually support. And after running this function, setting the GPUs, it can be run like any other function. In here, we'll also incorporate later this TensorFlow serving function and create our pipeline like we've seen before. So this time we set the image height and width as parameters and deploy a pipeline, which will download our images from our S3 bucket, run our training, and as we said before, simply defining the input of the training function as the output of this OpenArchive function will make it run after that on the pipeline. So this will run our training function, and then we will deploy it, taking the model from the training function, passing it to our deployment model endpoint, running it. And when we run it, this will also run on top of our pipeline. We can see that we download the data set. We have our training function. We can see the code, all the different logs running from this function. We can see our summary. And if we go into the project, just as before, we can see our downloaded file, and we can see our training with the inputs, the artifacts, the results of our training, the logs, and all the different pod configuration, and the function that is tracked for us. So simply by changing the runtime to our MPI and adding the Horvath optimizer to our TensorFlow code, we were now able to run on a multi-node, multi-GPU way with MLRun and track everything directly. Let's see how easy it is to really deploy and use this function. Just so you see an example for TensorFlow server. Okay, as we said before, we have our TensorFlow model class based on our V2 model server. We tell it how to load our model. So we have our image preferences here that we can get from the environment. We have our classes map that we want, and we load the model using the TensorFlow keras load model function. We add some pre-processing to the function, resizing it to our wanted size. And at the end, we predict it and return our predictions. And just by creating this simple model class, as we said, we've gotten an enterprise grade function model endpoint that we can use directly in our different services. Okay. So I see that we are about to hit the time limit. Are there any questions, any specific topics maybe that someone would like to talk about?
So thanks so much, Or. If any more questions come up, please feel free to reach out to us in the Slack channel. And also we'll be sharing this recording if you want to just go over everything that Or just showed you. Anything else, Or?
No, I hope that everything we talked about makes sense. If there is any help that you need, you can contact us on the MLRun channel, our Slack channel, as you're probably already on. And I really hope that you'll have a lot of fun, both in our hackathon and also using MLRun, and it will help you really deploy your models and be productive.
Okay, thanks everybody. Thanks so much for joining us, and good luck to everyone.
Great. Bye, everyone.
Okay, bye.
Thank you.